In this tutorial, we are going to talk about the dual nature of light. So is light a particle or is it a wave? So first we'll talk about how we prove that light can travel like a wave. And then we'll talk about proving how light can transfer its energy as if it's a particle. And then we'll talk about how to calculate the energy of photons. So in order to talk about light and how it acts like a wave, and when I say it acts like a wave, what I mean by that is that it's got a measurable wavelength and frequency. So it travels like this, just like a water wave. How do we know that? We know that because we can look at how it behaves under certain circumstances. So for example, water. Let's talk about water and how it behaves. We know that water travels in waves. We can see that it travels in waves and has a crest and a trough. If we took water and we dropped a stone here and a stone here, you would get these circular ripples that ripple out. And when those circular ripples hit one another, you start to get what's this interference pattern of diffraction. So this picture is a little clearer than this one. And if we were to put a screen up where these little interference patterns hit, we would notice that we would get spots where the crest would hit and spots where the trough would hit. Spots where the crest would hit, spots where the trough. Crest, trough, crest, trough. And it would look something like this. We would get these interference patterns where you get a crest and then a trough, and then a crest, and then a trough. So we know that water does this. So what we did is we took light and we shined light through a screen that had two little holes or slits in it. This is called the double slit experiment. And when we shine light through that, if light acts like a wave, you are going to get an interference pattern just like you would if you had two waves of water running into each other. And if we put a screen up at the end of, where these waves hit, we should get a pattern much like we get with water, where you get a dark spot and a light spot, or a crest and a trough, a crest and a trough. And that's in fact exactly what we get when we shine light through a double slit in a screen and then see what happens on the other side. And this proves that light travels as a wave, because if it didn't travel like a wave, if it traveled like little particles, well, think about if you just shot a whole bunch of like BBs or rolled them through a screen with two slits, they would just roll straight through and then hit the screen, straight on, and you would just get two little dark spots where they hit. And that's not exactly at all what we get when we pass light through this double slitted screen. We get an interference pattern that looks much like what a wave would do, not like what particles would do. So where did we get this idea that light isn't just a wave? Well, we got this idea through some more experiments. So if light actually travels like a wave, and it is a wave, then it should transfer its energy like a wave does. And what I mean by that is that an energy of a wave is due to its intensity, meaning that for light, the brighter a light is, the more energy it should have. And the fact is that's actually not true. So if you think about water waves, and you're sitting on a pier and along comes a big wave of water, the taller the wave of water, the more energy it's going to have, the more intensity it's going to have, and it's going to knock you off the pier. And the same would be true with light. If light travels like a wave, which we know that for sure it does because we proved it with the double slit experiment. So if light travels like a wave and it hits electrons in a sheet of metal, then it should eject the electrons in this. So just like what this picture shows, it shows light traveling as a wave, it hits these electrons and it knocks them out of the sheet of metal. And that is absolutely true. That happens, and we've been doing experiments with that for a very long time. So that being said, if you increase the intensity of the light, if you make the waves taller, then there should be more electrons knocked out of the sheet of metal. But that doesn't happen. When we increase the brightness or the intensity of those rays of light, we don't see more electrons being ejected from the metal. In fact, it doesn't make any difference at all. However, If we increase the frequency of that light, making it, the waves happen more per second, we actually do eject more electrons. So what that tells us is that light doesn't transfer its energy to the electrons like light or like a wave should. Instead, it's transferring its energy to those electrons like a particle. So think of it like light is acting like a little pool ball, like a little cue ball. And when you knock it into, say, another pool ball, what's going to happen is it's going to transfer its energy to that pool ball and make it move while the cue ball stays still, right? Well, it'll stop the cue ball and it'll transfer all of its energy to the pool ball and make the pool ball move. And that's how light is transferring its energy to an electron. And by the way, this has a name, this little thing that we've discovered about light. This is called the photoelectric effect. And it's very useful. The photoelectric effect was proven by Einstein. He actually won a Nobel Prize for it. And we use it in photocopiers, but for you probably would recognize this as what we would use in the solar cells in your calculator. So, you've got the incoming light from, say, the room, light, and then the little cell or the solar cell in your calculator has electrons in it. So it's like a little flat piece of metal, and the light will knock the electrons out. And then if you can get these electrons to travel through a wire, that'll power your calculator. So, or, a solar cell, a larger solar cell in, say, a home, works exactly the same way through the photoelectric effect. And you should also know that these little packets of light, so since light acts like a particle, we have a name for a particle of light. It's called a photon. So, and it's quantized. And what that means, if you remember what a quantum is, that just means that the energy in a certain frequency of light, those little packets or photons have different amounts of energy depending on their frequency. So whether or not they're a microwave or an ultraviolet ray or the different colors of light like red, orange, yellow, green, blue, indigo, or violet, those all have different quantized amount of energy because they're different kinds of photons. They have different amounts of energy. So we can summarize our findings for the dual nature of light as this. It travels like a wave and it transfers its energy like a particle. All right, so let's talk a little bit about how to calculate the energy of light photons. To do that, you need this equation. The energy of a photon is going to be equal to h, which is called Planck's constant, which is named after Max Planck. Max Planck was a scientist that kind of started this whole experimentation and study of the particle nature of light. So we name the constant after him. Planck's constant is designated as a little h, and its value is 6.63 times 10 to the negative 34 joule seconds. And just it should be mentioned that a joule, or capital J, is our way of measuring energy. So it's a unit for energy quantity. All right, and then of course you have the little nu, which is the frequency. And as we just talked about, the frequency of a wave or of a particle of light is what gives it its energy, or part of what gives it its energy. So if you know the frequency, you can multiply it by Planck's constant and calculate the energy of a photon. So for example, I might ask a question like this. What is the energy of a photon with a frequency of 4.25 times 10 to the 14th hertz? So you would just plug that into this equation. The energy of your photon is going to be Planck's constant, which is 6.63 times 10 to the negative 34 joules seconds. And you're going to multiply that by your frequency of 4.25 times 10 to the 14th hertz, which is, by the way, waves per second. So you can see that your second cancels, and you're multiplying Planck's constant by the frequency, and you're going to end up with this number, 2.82 times 10 to the negative 19 joules per wave, or joules wave. But we're just going to go with joules. And that's going to be the answer to that question. All right, so we have covered the dual and particle nature of light.